Morning, everyone. My name is Chris Milner. So I'd like to start by acknowledging my collaborators here who have contributed significantly to this project and our funding sources who have helped support this research. So in this talk, what we'll be looking at is how we can try and use geodetic imaging data to understand what controls the variation of displacement across surface ruptures and how we can use those data sets to inform probabilistic models of distributed rupture. So we know faults aren't simple planes, they're complex zones of damage. And so in this example here, a fault zone is typically made up of a principal slitting surface at its core that's usually surrounded by ultracataclysite or cataclysite material. And as you get further away from this fault core, you typically find a decrease in the density of fractures. So here we'll be talking a lot about off-fault strain, off-fault displacement. And so what we mean by this, because it's quite a vague term, is any strain that is exceeding the failure strength of the material. So we're talking about large strains that's causing the rock to fail. So we're not dealing with infinitesimal elastic strains, we're dealing with inelastic strains that's being accommodated away from this primary slitting surface within the damage zone, the fault zone. And so it's important to try and understand what is the amount and width of distributed deformation, because it can affect how we estimate long-term slip rates. It's been shown to affect the ability of ruptures to propagate through the near surface, rupture velocity and directivity, and poses a significant hazard to nearby infrastructure, such as an example here of the Trans-Alaska Pipeline crossing the Denali Fault. Okay, so some of the questions we'll try and answer in this talk is what affects the width and variation of displacement across surface ruptures, and how can we try and improve probabilistic fault displacement hazard models using geodetic imaging data. And so what we'll use today are image correlation to try and measure the near field coseismic deformation of the 2019 Ridgecrest earthquake sequence. And so, okay, so what is PFHA? It's basically a probabilistic approach to characterize the annual rate you expect to exceed some amount of displacement at a given location. And so the way it works is you typically measure offsets displacement across a fault rupture in the field, and you compile all of those observations for different earthquakes, and you try and understand how the displacement attenuates either along a rupture or across a rupture. So in this example here, it's showing the distance away from the primary fault surface. And so you're trying to characterize the attenuation of distributed displacement away from the primary fault surface using these field observations. And so you can think of PFHA as being analogous to PSHA, really because actually PFHA takes the probability theory from PSHA. But in PSHA, what you're trying to do is you're trying to constrain this ground motion prediction equation. So how does some seismic parameter, say in this case, spectral acceleration, attenuate with distance away from the source? And so in PFHA, what we're trying to do is similar in that we're trying to characterize how fault displacement attenuates away from the primary fault using fault displacement prediction equations. So once you have those fault displacement prediction equations constrained, you can then come up with hazard curves once you've made some assumptions about the temporal characteristics of slip release over time. And this tells you how often you expect to see a certain amount of displacement or exceed a certain amount of displacement at your location per year. And then you can also come up with hazard maps, the rupture. So how do we measure the 3D surface displacement pattern? So Saif Ati here, who's part of our group, has really been leading the effort in trying to develop the next version of the optical image correlation technique. So traditionally, what you do is try and resolve the lateral shifts of features from before and after satellite images. And so this gives you the horizontal 2D component of surface motion. What Saif has been working on is implementing a ray tracing approach to try and essentially triangulate the 3D position of each pixel from the intersection of the look vectors of each satellite taking an image. And so if you know the satellite position, which we do, and the look direction, you can then calculate the 3D position of each pixel. And if you have this configuration before an earthquake and after an earthquake, you can then track how that pixel moves and is translated in space over time. And so what Saif has also been working on is automating this approach. So now we can actually use images from different satellite sensors. And so this is really really great because it now allows us to have a greater number of look vectors to better triangulate the position of our pixels. And then we also have implemented an independent component analysis filtering technique to try and pick out the common tectonic signals, especially that are useful when you're using a mix of different images from different sensors. And so we also received funding to write this in Python, so I hope we'll have an open source version of this technique coming out soon. So this is the 3D displacement result we have for Ridgecrest. This figure shows the motion in the north-south direction, the east-west, and the vertical component of motion. You can see here we resolve both the forward shock rupture and the main shock rupture here. And so from these displacement maps, what we can do is calculate the 2D strains from the 3D displacement pattern. So here's just showing the displacement gradient tensor for the for 2D that we use to calculate the 2D finite strain. And the finite strain just differs from the infinitesimal strain in that it just includes these higher order terms here. And because we're dealing with large strain, it's not really appropriate to assume infinitesimal strain in this case. And then we can calculate the finite dilatation, and that tells us which parts of the fault zones are contracting or undergoing extensional fault perpendicular strain, or aerial strain really. And so here in the north, we can zoom in and have a look at this in detail. So this is an example showing the horizontal component of motion. These vectors are showing the direction of motion, and the colors show the amplitude in the northwest southeast direction. So you can see along this segment here, these vectors are kind of, you can see this differential motion shown by these vectors. Then if you go along this transtensional bend that kind of bends to the right, you can see these vectors are now diverging away from each other. And in the vertical displacement map, you can see this part of this block is subsiding down. And so if you look at the dilatational strain, you can see here the significant positive dilatation indicating extensional strain occurring. And if you look at this segment that is undergoing mostly shear, you can see actually there's a variation in dilatation from contraction to extension. We have these kind of subtle releasing and restraining bends along this rupture that undergoes mostly shear. And so you can see again something similar here, where this component we have in this figure, we have this right bend, this transitional bend, where the vectors are diverging away from each other, vertical subsidence, and then positive extensional strain. We see significant widening in the fault zone into this transitional bend. And so what we can do is this displacement maps is measure profiles that show the distribution of displacement across the fault zone in the parallel, perpendicular, and vertical component. And so it's interesting if you compare the fault parallel motion, the total displacement from our optical maps, compare that to the field observations, you can see it's about ½ meter difference between the two. And so this difference could be attributed to measurement uncertainty, but actually this discrepancy is pretty systematic along strike, and other studies have shown this difference too. And this is really attributed to the larger aperture measurement that you can use from these optical displacement maps. And also we can then look at how the strain attenuates or varies across these different ruptures. You can see these different segments. So you can see here on this what we'll call the shear segment is a very narrow fault zone, and then within this transitional bend, you can see the fault zone widens. And so if you look at the average strain profiles for these two segments, compare them, you can see that this red shear segment has very high strain localized fault zone, where you have very fast, rapid attenuation of strain, whereas in this transitional band you have a lower, slower attenuation of strain away from this the primary fault within this transitional band. Okay, so we've seen some examples of how the fault zone width strain zone can widen in areas where the material is experiencing extensional contractional strain. And so what can we do with these profiles? How can we use them to inform probabilistic fault displacement hazard models? So what we do here is we draw profiles across the fault. We take lots of these profiles along the rupture, and then this is kind of an example showing some of these profiles here, showing the variation of displacement across the fault zone. And so what we want to do with these profiles is try and understand and capture the variability in the total magnitude, so the amplitude of these profiles, and then the variability in the distribution or the width of these profiles, and then feed those to constrain fault displacement prediction equations. And so we've done this for 14 different strike slip continental earthquakes, ranging from magnitude 6.1 to 7.9. And so this is an example here showing the compilation of all these profiles together, where we're trying to understand, is there a kind of a common attenuation of distributed displacement away from the primary fault core? So the idea, really, question here is, can we distinguish an appropriate functional form to describe that attenuation? And we find that given the significant scatter in the data, it's difficult to understand which functional form fits significantly better than any one other. And so what we find is that comparing an arctan and error function Laplace function is that an error function provides the lowest overall misfit. So that's what we've gone for now. And then second, what we find is that, as I showed before, we showed that those profile, the strain distribution and displacement can vary significantly when you're in these transtensional bands. And so what's interesting is if you separate the data when you're constraining these fault displacement prediction equations into structured simple and complex, you can reduce the variability by about 45%, which is quite significant. Okay, so now we have those fault displacement prediction equations constrained. We can then come up with an estimate of a hazard estimate. And so this is a really simple example, kind of toy example, showing a scenario where we have a building that's located 15 meters away from a fault. And we're assuming here a scenario event magnitude 7.3 and a slip rate of 3 millimeters a year. And so this example here shows a hazard curve illustrating the effect of your building site being located close or near to the main fault rupture. So 25 meters or 150 meters away, you can see as you go further away, the annual rate you expect to see a certain amount of displacement decreases quite significantly, which is what you expect. And that's coming from those fault displacement prediction equations. And so we can also look at the effect of assuming different different functional forms for those fault displacement prediction equations. We can see that there's not much of a difference between the error function and the Laplace, which isn't surprising given they're pretty similar functional form. But an arctan can produce, in some circumstances, a fairly big difference in the hazard, especially when your building is located kind of on the periphery of a fault and where that sense of attenuation can differ. And then we can also look at the effect of if you use fault displacement prediction equations in different regions of a rupture. So here, this is the hazard curve where we've used the fault displacement prediction equations in a structurally simple part. And if you use the fault displacement prediction equations in a structurally complex part, you can see it's quite significant difference in the hazard expected. So just to conclude, we've tried to show some evidence that we observe wider fault zones within areas where the material is experiencing increasing amounts of extensional strain. If you're interested in stresses and how we go beyond strains, the stresses, please see our poster number 109. But there are a lot of other factors left to explore in terms of what controls the width and variation of displacement along faults. And there's a lot of ongoing research into this problem. I suggest you look at these really great studies if you're interested in learning more. And so we've shown that these geodetic imaging data sets could be useful to try and provide spatially dense measurements with uncertainties that can be quantified. And these observations too can also help move towards a non-ergodic PFDG approach, where these data sets can help provide constraints for physics-based dynamic rupture simulations. So the study that just came out by Wang and Goulet that did kind of just this exercise. And so how can we perhaps further reduce the epistemic uncertainty in PFDG models? Well, one way is to try and better understand what factors of control width and variation of displacement along a cross rupture, because this can try and help reduce the scatter in these fault displacement prediction equations. So with that, I'll leave it there. Thank you very much.